Okay, so do you remember, and it was a long time ago, but you did it last year too, tangent lines. Do you remember that? I wore my shirt last time. I should have worn it today. Sometimes I go off on a tangent. Anyway, do you remember how you can use the tangent line to approximate values on the graph as long as you pick a number that's close enough to the point of tangency? Like if your point of tangency is 1, you can approximate like 1.1, 1.2, etc. But a tangent line, I mean, it's linear. It's only to the first power. It's not a very good approximation, right? So what we're going to do now, and they're called Taylor polynomials. So instead of something linear, we can do something with a higher power, and you get a better estimation of your graph. Does that make sense? Higher the power, the better it is. In fact, I think I wrote that on here. Yeah, the higher the degree for the polynomial, the better your approximation. The closer your input value is to your, we can't call it a point of tangency because it's not a line anymore, but closer you are to the value you're centered around. We say it's centered around C. C is the center. The closer you are to that, the better your approximation is going to be. All right. This unit in a nutshell, we're going to cover like most of what you need to know right here and now, is this. If you want to put like stars next to this, to get the coefficients, it's the nth derivative. When you do a first derivative, you put one little like slash there. A second derivative, you put 2. You could put 3 for the third derivative, but usually after 2, we just put the number there. So like a third derivative would be f3 of x. Because if you get up to like the 7th or 8th derivative, you're not going to put like 8 slashes. Do you know what I'm saying? Anyway, it's your nth derivative over n factorial, or n. Okay, this is the important thing to know. So a Taylor polynomial looks like this. You have your nth derivative over whatever that factorial is, x minus c to that power. So it's the 0th derivative, which is just the function, right, over 0 factorial x minus c to the 0. First derivative over 1 factorial x minus c to the 1, and so on. It's just a pattern. Now, if it's centered at 0, we call it a Maclaurin polynomial. Everything in math either is what it sounds like or it's named after the person that came up with it, right? So this is your Taylor polynomial. Maclaurin simply means it is centered at 0. For some odd reason, they will write all the time on the AP exam, like every problem, they'll say Taylor polynomial centered at 0. And it's like, we have a word for that. Just call it Maclaurin polynomial. I don't understand why they do that. But anyway, Maclaurin means centered at 0. We're going to start out with a real easy one, which is e to the x. E is the easiest function because what's the derivative of e to the x? So, okay, and we're going to do derivatives here, so I picked an easy one to start out with. Off to the side, and I just always do my derivatives as a margin problem. Off to the side, we're going to do our first derivative, and we're going to do our second derivative. Read the rest of the problem. Why am I stopping after the second derivative? Why do I not have to? Second power, okay? And both of these are e to the x. We kind of didn't need to write them for this, but I'm trying to get you in the habit of how we do these problems. If it's any harder than e to the x, you're going to need to write it out, okay? So let's go ahead and set it up. We are going to do, what are we doing? Maclaurin. So we're going to have e to the, I should label. What degree are we doing? Second. So we write it like this. P for polynomial. So we're going to have e to the nothing over 0 factorial x to the nothing. All right? Plus, and then you're going to do your first derivative, which is also e to the x. All right? So it's going to be e to the first over 1 factorial x to the 1. And then anyone want to give a try what the last one would be? Yeah, e to the second over 2 factorial x squared. And then we're going to just clean that up a little bit. All right, that looks kind of a mess. So we're going to just simplify. E to the 0 power, anything. Well, let me answer this question before I do this then. Go ahead.
On the formula sheet, it said it's f prime and f double prime of 0 and so on. So is it like f prime of 1 or is it e to the 0?
Oh, did I? Oh, you're right, 0. I'm sorry. Too much to look at. I apologize. Yes, this one is 0. I'm so sorry. Thank you. Crisis averted. I'm glad you said that before I did the next step or the whole thing would have been wrong. I'm so sorry. Centered at 0. Apologize. I messed up the first one and I even said it was the easiest one. Dang, that's embarrassing. That's all right. I'll persevere. All right, what is anything to the 0 power? 1. So this is 1. Weirdly, 0 factorial is also 1. It can't be 0. That wouldn't make any sense. And then this would also be 1. So that entire first term is 1. This would also be 1 over 1. But then we actually have something there, which is x. So 1x. And then this would be 1 over 2 factorial is just 2, and then x squared. So this is our answer. So remember how I said we used to use tangent lines? This gives you a better approximation of a graph. And where we're headed next time, if you take this out infinitely, an infinite series, you know, sigma and stuff that we just finished, instead of approximating the graph, it will equal it exactly. That's what a power series is. So we're not there yet. We're going to do this first, but that's where we're headed. Are the factorials what? Multiply. Well, they're being divided. They're in the denominator. Hold on. We're going to do a couple more. We only did one problem, right? Now this says find the nth degree Maclaurin polynomial. What I'm asking you to do is continue the pattern. So we're going to have 1 plus x. Now I would write this next term, this is typically how you see it, as x squared over 2. Let me finish this thought. I didn't see your hand until I was halfway through this. What would the next one be? I just want to see if you can continue the pattern. That's what we're doing here. It's over 3 factorial. Good. Okay, we just didn't put, I guess you could put the exclamation on that. It was 2 factorial. It's just 2 factorial is 2. All right, let's see if we can do a couple more. It would be x to the 4th over 4 factorial. Good. And then what they ask you to do is write like the general term, which would be like what has n in it. So this is x to the nth over n factorial. Good. Perfect. We got there. Hold on. Jack had a question first. And then I will take your question. This one?
Yeah.
Because it says Maclaurin polynomial, and that means centered at 0. Maclaurin means centered at 0. We'll do one that's centered somewhere else. I think the next one I have is centered at 3. So you'll see how it looks different. No, it's for all values of n. Every value of n ever. Yes, keep going until it starts making sense. Usually about the 4th term, and almost always what the directions on the AP exam will say, and you'll get used to this because you'll see it a million times, write the first 4 non-zero terms and the general term. So usually if you get to about the 4th one, that's where it starts making sense, or like the pattern will start to click for you. So usually at least 4 is what we want to do. All right, so let's try one that's not centered at 0 so that you can see how it's different. We want to go all the way to the 3rd degree. I have f prime and f double prime just for the sake of being super thorough, and so you can see how we usually write it. When you get beyond the 2nd derivative, this is how we would write the 3rd derivative, but it is still just going to be e to the x. Again, I was starting out with like a easy pattern for us. But again, if it's not e to the x, you would definitely need to write it because it's not going to be the same thing. Yeah. All right, so we're going to do a, what degree? All right, 3rd degree, centered at 3. So using our original function, it would be e to the 3rd over 0 factorial, good, x minus 3 to the 0. It's centered at 3 now. So every single parenthesis is going to have x minus 3 in it. All right, let's try the next one. First derivative is still e to the x. So it's going to be e to the 3rd over 1. Good, you guys are getting it. X minus 3 to the 1. Even though I messed up the first problem, you still got it. So I'm very proud of you. All right, and then the next one would be e to the, they're all going to be the same, all right, over 2 factorial, x minus 3 to the 2nd. And then can we just all go ahead and write one more? Because all the derivatives are e to the x. They're all the same. And it's centered at 3. So we plugged in 3 for all of them.
Oh.
This one was 0, so we plugged in 0 for all of them.
Oh,
okay. Wait until we do one. See, you guys were getting hung up on it because the first one I did was centered at 0. Now you're seeing one that got centered somewhere else. When we flip over, we'll do one that's not e to the x, and you'll get to see how that's different. I kind of staged the notes like that on purpose so that we can build on itself. All right, let's just clean it up a little bit. What will that first term sort of boil down to here? Well, 1 e cubed. You can put a 1, I guess, if you want. Plus, all right, this would be e cubed times x minus 3. This one would be e cubed over 2, x minus 3 squared. You know, I will say often, though, it's better to leave the factorial in there because when you go to write a general term for something, for example, if you've simplified 3 factorial to 6, you can't see what the factorial was anymore. So sometimes you're better off just like literally leaving it alone. Actually, I'm not even really going to do anything to this one. Because if you had to write the general term, it's almost better if it's not. So the only terms we really cleaned up were the first 2. It's good to know your factorials. Like 3 factorial is 6. Do you know 4 factorial? 24? Okay. 5 factorial is 120. Okay. I know I'm up to 5. I feel like it's good to just know a few of them. So, all right. So for this one, it's not e to the x this time, so all your derivatives are going to be different. We want to find a 4th degree Taylor polynomial centered at 1, and then we're actually going to use it to make an approximation, so I'm going to have to pull up the calculator. Off to the side, I do it like a margin problem. We're going to get our first derivative and our second derivative and our third derivative and our 4th derivative. And why am I stopping at the 4th power? Okay. Now you're going to have to come with me mentally on this because there are going to be some negative exponents, just as a heads up, like your fine print. I'm going to talk you through it, but we're not going to write out every step because this is BC, and I think you're at a level where we can kind of hold some of it in our head. What is your derivative of ln x? Yep. Okay, we're good so far. Now, in your mind, I want you to think of that as x to the power. Good. Okay, cool. Derivative. You would bring the -1 down, and it would drop to a -2. So we're going to write that as -1 over x squared. Good. Perfect. You'll hopefully see the pattern soon. Now, think of that as -1 x to the -2. If you bring the -2 down, it will become +2, and then the power drops to -3. It feels like you kind of have it. Do you want to try the next one? You want to think of it as 2x to the -3. It'll be -6 over x to the 4th. Cool. Just for the sake of trying another one, what would the 5th derivative be? It would be +24. Perfect. You got it. All right. Let's go ahead and write out our polynomial. It's going to be about this big, okay? So write small. Okay? It's going to be very large. I'm going to start all the way at the edge of the paper. We're doing a 4th degree, and it is centered at 1. Cool. So we're going to have ln1, which is, I'm going to just write it out so we have the pattern, ln1 over 0 factorial x minus 1 to the 0. Plus. All right, now we're going to plug 1 into our first derivative, which would just be 1 over 1 factorial x minus 1 to the 1. So, all right, now we're going to plug 1 into our second derivative. Perfect. -1 over 2 factorial x minus 1 to the second. It's a little bit of writing, but it's very much just pattern driven. This is my pep talk. You can do it. It's just a pattern, right? Plug 1 into your third derivative. 2 over 3 factorial x minus 1 to the third. And then one more. If you plug 1 into your fourth derivative, Negative 6 over 4 factorial x minus 1 to the 4th. Let's simplify it down. I know I just got done saying sometimes it's better to leave the factorials in here because I am going to go, well, I can type them in the calculator. Never mind. What is this entire first term going to go to? Yeah, that whole thing's 0, so that's just gone. And again, they will typically say write the first 4 non-zero terms. So that one wouldn't count. If you're on the AP exam, you have to get 4 terms that aren't 0. This would just be x minus 1. So it'd be minus a half x minus 1 squared. Plus, oh, you know what? I did want to simplify these fractions because I want you to see what happens with these. This would be 2/6, which would be good 1/3. Because do you see what's happening? A little bit? Okay. And then minus, this would be 6/24, which is 1/4. And also, what kind of series would this be if we kept it going forever? So alternating, cool, because that's going to come up. Go ahead. We did ln of 1, and ln of 1 is 0, so that entire term went away. So we just didn't write it. We're using our derivatives. So for that term, we used the first derivative. We plugged in 1. For this one, we did the second derivative, we plugged in 1. For this one, we did the third derivative, we plugged in 1. And for this one, we did the fourth derivative, we plugged in 1. Is that cool? Okay. Now, it wants us to use this to approximate ln of 1.1. So if you will humor me and actually help me type this, because it's going to be a bunch to type, and help me to not make a mistake, or just make fun of me when I do. Right? So don't look away. I felt you all just decompress. She's going to do the work for us, so we don't have to do anything. All right, what am I going to type? 1.1 minus 1 would just be 0.1, okay. Minus, what comes next? 1/2, cool. Parentheses, 1.1 minus 1, which is just going to be 0.1, cool. To the second, plus 1/3, and then I can just do, hold on, okay, cubed, and then it's minus, right? Oh, geez. Hold on, the fourth. Okay, it's 0.095, and then we're going to go out there and just stay together because I have to do attendance once we get out there. 0.095. All right. Now, did you notice how when I was typing that in the calculator, I had to keep on doing 1.1 minus 1 and 1.1 minus 1, which was like a little bit annoying. Okay. So if instead you wanted to use Maclaurin, which means centered at 0, then you would just plug in 0.1 instead, and it would be a little easier. Okay. So if instead we wanted this centered at 0, imagine plugging x plus 1 into every single one of these. Well, what would happen? You would have x plus 1 minus 1, and it would just come out to be x. So it would look like this. So it's exactly what we have written right up here, but centered at 0 instead. And I'm not going to make you watch me type it in because of the fire drill. But if I plug 0.1 into that, what do you think we're going to end up with? 0.095. It's going to come out the same both ways. Okay, so just for what it's worth. I do want to do one that's a sine or a cosine because you are going to see it on your delta math. Now, this is a 6th degree. You're probably like, why is she taking it out so far? I have a reason, and you'll see why in a second. Off to the side, we're going to do all 6 derivatives. You're going to be okay. It's not going to take that long, I promise. Okay? Are you sure? Okay, it's not a big deal. All right, derivative of cosine. Good, negative sine. We're going to just churn these out. Derivative of sine is cosine, so this would be negative cosine. All right, again, you will see why I'm doing this. Like, why is she taking it out so far? You're going to see, okay? That'll just be sine. Good job. Fourth derivative is just cosine. And that brings you back where you started. So now we're going to just cycle through a little bit further. So fifth derivative would be negative sine, and sixth derivative would be negative cosine. Thank you for hanging in there with me on that and having a good attitude about it. I do have a reason, okay? You know by now that I don't believe in like nothing work or busy work. Like I have a purpose behind everything that we're doing, right? So we want our sixth degree polynomial. And we're going to center it at 0 because it says Maclaurin. All right, so we're going to plug 0 into here. Cosine of 0 isn't 0. Cosine of 0 is 1. Good, so it is 1 over 0 factorial x to the nothing. Plus, now we're going to do our first derivative at 0. However, what is sine of 0? Sine of 0 is 0, so that's going to literally just be nothing. I'm going to skip it, right? We're on to the second derivative. Second derivative at 0. Cosine of 0 is 1, but this is actually going to be negative 1. Good. So negative 1 over 2 factorial x to the second. No, we did x to the 0. This one would have been x to the 1, but we skipped it. And then so this one's x squared. So now we're on the third derivative, but sine of 0 is, I'm not going to take any questions until we finish this pattern. I can't stop in the middle or we're going to lose traction, right? Fourth derivative. Cosine of 0 is 1. It'd be 1 over, good, 4 factorial x to the fourth. Now we're on the fifth derivative. 0, and then the sixth derivative, it's going to be negative 1 over 6 factorial x to the sixth. Go ahead. Or do you want to think about it? You kind of just have to let it marinate for a second. All right, so let's write it without all the like parts that are missing. All right, this first term would just be 1, all right, minus 1 over 2 factorial x to the second plus 1 over 4 factorial x to the fourth minus 1 over 6 factorial x to the sixth. What would the next term be if you had to do it? Would it be positive or negative? Positive 1 over 8 factorial x to the 8th. And then it would be minus 1 over 10 factorial x to the 10th. Do you see what's happening there? I just want you to understand the pattern. Again, this is the reason why they will typically say, write the first 4 non-zero terms. The 0 terms don't count. Okay? And then the last one I do want to do, because this does show up in the AP exam and it's weird. I'll be honest, I don't really love. Oh, go ahead. Maclaurin means centered at 0. That's just by definition. Otherwise, they're going to tell you. You won't be able to miss it. It'll say centered about some number. C equals something. Yeah, they have to tell you. You know, they can't just not tell you. All right, so we have e to the x times f of x. E to the x, and we only want to go up through what power here? What degree does it say to go up? 2, second power. We already did that one. It's right here. Do you see? So just copy that over. 1 plus x plus 1/2 x squared. We already did it, so we're not going to do it again. Now, for f of x, we're going to use these numbers right here and do our pattern, all right? So it would be 6 over, good, 0 factorial x to the 0, cool. And then the next one, first derivative is 3, so it'll be plus 3 over 1 factorial x to the 1. And then negative 2 over factorial x to the second. All right, so let's clean that up. The first term would just be 6. And then this one would be 3x. And then this one would be minus 2 over 2 would just be 1. And then x squared. So here's what we have to do with this. And we're done with any calculus. All right. A lot of this isn't calculus. It's really just algebra to begin with. Is we want to multiply those two things together. Do you see how it says e to the x times f of x? Here's the thing, though, and this is why these problems kind of annoy me. We're going to multiply all of this times all of this. But you can't go past power 2 because it says second degree. So if you ever get a term that's past a second degree, just forget about it. Okay? So I would distribute the terms one at a time. First, let's distribute the 1 into here. If you distribute a 1, it's just going to be, like that. So 6 plus 3x minus x squared. And I didn't go above power 2, so we're good. And then you would distribute x into all three of them. Or maybe not. We'll have to see. It would be 6x plus 3x squared. And then it would be minus x to the third. And so we're just not going to do that one. You just can't go above power 2. And then we're going to distribute 1/2 x squared to probably not everything. All right. If we distribute it to the 6, that would be 3x squared. And I think we can't even go any further than that, right? All right. And then we're just going to combine like terms. Probably been a long time since you heard that. We're back to like very basic algebra here. So it'll be 6 plus 9x. And then what is that? 6 minus 1, so 5x squared. So if you have to multiply two things together, but they say they want a second degree, just don't go above 2. Okay? And you still have 10 minutes. You could do a problem, okay?